The objective for our project was to design a wing structure that would meet certain requirements we were given, where we'd use various tools to improve our design over time.
Looking at the requirements of the wing, since we were told the length and the airfoil we'll be using, our main focus would be on its requirements for the wing spar.
Our initial sketches were various cross-sections for our wing spar and ideas on how we should join the wing spar together. We decided the best cross-section was a rectangular one, as it is good for both bending and torsion loads.
We were planning to test out both a rectangular beam and an I-beam. This meant that we would need to work out the single moment of area for an I-beam to compare the two. We did this by splitting the I-beam into 3 rectangles. In addition, we worked out an expression for the bending moment, then we would be able to work out an expression for the deflection.
To model the wing spar, we assumed that the force acting on the wing was concentrated at the tip of the wing. We then also said that the wing spar was fixed to the root, so it was essentially a cantilever beam. This meant that when we plotted the bending moment diagram, the largest bending moment would be at the root.
Since we already had a general equation for the bending moment and deflection of the beam, we could easily put the formulas into Excel so we would not have to do them by hand every time. This proved to be a useful tool when we wanted to try various designs.
In addition, as we were modelling the spar as a beam, we had to make a few assumptions so we could use beam theory. For example, the beam had to be isotropic, or the properties of the beam would vary along the beam.
Initially, we had used estimates for the material properties of the formwork, but when we worked out the density of the actual formwork, the values were slightly different, so we had to adjust our values throughout the process. Since the formwork was 5 mm thick, the thickness of the walls had to be a multiple of 5 to make manufacturing easier.
The first test we did was between 2 beams, one made using hot glue and one using tape. From the results we can see that the beam made using tape held almost double the weight of the beam made using glue, but the trade-off was that the mass of the beam had almost doubled.
Next, we tested a wide flange I-beam and a narrow flange I-beam. Looking at these results alone, we can see that the I-beam weighs less than a rectangular beam and can hold a similar load.
However, if we compare I-beam and a rectangular beam under a torsional load, we can see that the rectangular beam holds significantly more weight and is less likely to exceed the torsional compliance.
To further test our beam, we used SolidWorks to simulate our beam under a load. This allowed us to easily change the dimensions of our beam and the material properties for a more accurate load.
Also, by simulating our beam under torsional load, we can see that by removing material it is more likely to break. So as a compromise, we decided to remove some material only from the most outer layer of the beam.
For our first iteration, our beam met all the requirements we were given. However, the beam carried a greater load than was needed and was quite heavy. This would suggest that there was excess weight that was not needed.
For our final iteration, we used a much smaller cross-section, and we also took some material from the side of our spar to reduce the total mass. This final spar managed to hold a load of 2.6 kilograms, which is just over the ideal load. As we are only using half the spar, the total spar should hold 5.2 kilograms.
Looking at our results, we can see that the rectangular spar would break at the roots where the bending moment is the greatest. Furthermore, if we look at the deflection graph, we can see that the deflection is generally linear until it reaches the ultimate tensile strength or the ultimate compression strength.
While our final design meets our initial requirements, there are still factors we could improve. For example, the spar still makes up over half the entire weight of the wing, and the foam starts to separate at the root of the wing.